All right, so looking at last night's homework, we had some linear and angular speed problems. All right, so let's go over those first. Okay, so first we have a Ferris wheel that has a 50-foot radius and makes 4 revolutions per minute. What is the angular speed of the Ferris wheel in radians per minute? All right, so for angular speed, again, all we need is the central angle that we cover, right? How many rotations divided by the time it takes to do it. So for the first problem, you don't need the radius. Okay, the radius doesn't come into play until we have our linear speed. So for our theta, again, 1 rotation, remember, is 2 pi radians. And we're doing that 4 times. Okay, so 4 revolutions in 1 minute. Every revolution is 2 pi. So the angle that we cover is 8 pi radians. The only unit of time that we're told is that it's 4 revolutions per minute. So t is going to be 1. So plugging in what we have, our angular velocity is 8 pi over 1. So we're going to have 8 pi radians per minute. Okay, so that one's pretty straightforward. As long as you find the angle, you're good. For the second part, okay, you had to take that, and now we want to find the linear speed. Okay, so again, linear speed, there's a few ways we can do it, but because we've already found the angular speed, we're just going to multiply the angular speed by the radius. So I have 8 pi. I'm going to multiply that by 50 feet. Okay. Now what happens when we multiply 8 pi? Now let me put the units. When we multiply the radians by the feet, that automatically removes the radians as a unit. Okay. By multiplying the radius, I'm finding the circumference pretty much, right? So we move away from radians and we go to whatever units that is. So I can multiply those two together. My linear velocity in terms of pi would be 400 pi feet per minute. But if you calculated that, that would be about 1,256.6. Feet per minute. All right, so you're moving pretty fast. But again, you know, it's not in miles per hour, right? Obviously, it's feet per minute. So you may be asked to convert, and actually we're going to do that for the extra credit for the last one. All right, but there's your answer for part 2. Any questions about the first part, the first question? All right, our second question. We have a Blu-ray disc. It's approximately 12 centimeters in diameter. The drive motor, the machine that you put the disc into, is able to rotate up to 10,000 revolutions per minute, right? Those things spin pretty fast. Find the maximum angular speed in radians per minute of a Blu-ray disc as it rotates. Right, so again, we're just going to use our basic angular speed. Right, so now we're making 1 rotation. We're doing that 10,000 times per minute. Right, so we're going to have a very large angular speed. Of 20,000 pi radians per minute. Right. This is pretty fast, right? But that's how DVDs and Blu-rays work. For the second part of that question, be careful. We want to find the linear speed. I give you the diameter of the disk. Okay, so our radius is half of that, 6 centimeters. So we take the 6 centimeters, we multiply it by 20,000 pi, and we get 376,991 feet per minute. No, I'm sorry, centimeters per minute. So the edge of that is moving fairly quickly. All right, so for the extra credit, I don't think we've gone over unit conversion. We might have at the beginning of the year. I forget, though. Let me write this down, though, and then we'll take a look real quick at that. Okay, so a quick lesson on unit conversion. I don't need this anymore. I want to know. All right, so we're starting with centimeters per minute, and I want to convert it to meters per second. So the way we do this is we use unit conversion to change the centimeters to meters and minutes to seconds. All right, and we're going to do one at a time. So I'm just going to rewrite so it doesn't really matter what you start with. I'm going to start with the centimeters. Okay, so I want to change centimeters to meters. So, well, first it would help to know how many centimeters are in a meter. Okay, so the conversion there is 100 centimeters to 1 meter. So how do I change that here? So what I'm going to do is I'm going to set up a proportion where the centimeter units eliminate each other. So I'm going to put 1 minute over, 1 meter over 100 centimeters. So now when I multiply these two, it eliminates the centimeter part, and all I'm left with meters over minutes, right? So what this is telling me to do is I have to divide this by 100. So that's pretty simple. All I have to do is move the decimal place over. So 376,000 centimeters a minute is 3,769 meters per minute. So then we want to do this a similar thing to the minutes. Okay, so we know that 1 minute is 60 seconds. So I want to get rid of this minute. So I'm going to put the 1 minute in the numerator, the 60 seconds in the denominator. So now the minutes cancel out. And again, I'm dividing this now by 60. So first I divided by 100. Now I'm dividing by 60. Okay, so we get about 62.8 And now my units are in meters per minute. Right, and then you can keep going if you wanted, kilometers an hour, which would be like a normal how cars move and stuff like that. You can keep converting like that. Right, so it may seem large here, right? 376,991 centimeters per minute. So if you really think about that, though, in 1 minute you're covering 300,000 centimeters. Well, 300,000 centimeters isn't, a centimeter isn't very big. But that converts to, oh no, I'm sorry, there should be seconds. 62 meters per second, which in reality is pretty fast. Okay, that's about how fast a car moves. So the edge of the disk that's spinning relatively is moving almost as fast as a car, right, on the highway. 62 meters every second. Okay, so I thought that was a neat little lesson. And again, like I said, I don't remember if we went over unit conversion in class or not. All right, so today's lesson, we are transitioning. So briefly today, this is going to pop up more in the future, but briefly today we are going to talk about the unit circle. And then that's going to lead us into our basic trig functions. Let me just sure. All right, so our unit circle, if you remember from algebra, is a circle that's centered at the origin, who has a radius of 1 unit, right? So over here we have the point 1, 0. Up here we have 0, 1. Over here we have -1, 0. And then down here we have 0, -1. So we've been talking about angular motion, okay, and rotation. So we're going to envision a point here, okay? This is our starting point, right? This is 0 degrees. This is 90 degrees. This is 180 degrees. This is 270, right? Or, you have your radians as you go around. So you're starting at 0 degrees and you're moving counterclockwise around the circle, right? And that's what we've been doing with our angular speed. We've been traveling in a circle. Well, if we're talking about the unit circle, okay, what we can do is we can map the x and y coordinates as they go. So I'm going to change my coordinate plane depending on what angle I'm talking about. So I do have a visual for this. Let me make sure I have. Yeah, good. All right, so I'll put this up with our, our notes today, so you guys can play with this later. Right, so here we have our particle, this yellow dot, and it's going to be traveling around in a circle. Okay, again, it's 1 unit long. So if we take a look at the x values of this function, right? So here my x value is 1. Right, so I'm going to mark this 1 up here. As I travel up, my x value goes from 1 to 0. Okay, so from 1, I'm coming down to 0, right? And up here, we said we have 90 degrees. 90 degrees is pi over 2 radians. As I continue to 180 degrees, my x value becomes negative, right? Over here, I have 0 to +1. Here, I have 0 to -1. So I'm coming down, and eventually I reach -1, okay? My x value of -1 is when we are at 180 degrees, right? Halfway across the circle, or pi radians. I continue around the circle. Now I'm back at my x value being 0. Okay, and down here, right, on our unit circle, this is 270 degrees, which is 3 pi over 2. Oh, you can't really see that. Oops, what did I do? Let me reset that. Nope. Right, and then we come back to -1. So what we just did there, when we mapped the x values of our function, okay, of this particle traveling around the circle, this gives me the shape of the cosine function. Okay, and it's, like I said before, it's, since we're traveling and we end up in the same spot, we call this periodic motion, right? So if this was, a constant something, right, it would just be repeating. And then what happens is, eventually after one full rotation, well then, like we saw, we just keep adding on, right? So this is 360 degrees. This would be, 380 degrees, and you would keep adding on, and this graph would just keep going on forever and forever, right? So the x values of our unit circle give us the cosine function. Well, let's take a look at our y values now. So here, my y value starts at 0. Okay, I'm on the x-axis. My y value gradually increases until it's 1. At 90 degrees, at 2 pi radians, my y value is 1. I come down, and at 180, I'm back at 0. All right, so from here to here, I go from 0 up to 1, back to 0. Right, and over here again, we have 180 degrees on the unit circle, which would be pi radians. Then I travel down to -1, so I go down to -1 there for 270 or 3 pi over 2, and I eventually come back to 1. So here are y values of the unit circle as I travel around give me the sine function. And that is one of the ways we come up with our trig functions, okay, our two basic trig functions, sine and cosine. Let me see, there was one other thing I had. Okay, so this kind of shows both happening at once. So there's a lot going on here, so I didn't want to show you this right away. Okay, so again, the red here is my sine function. The blue is my cosine function, as you can see here. So I'll put this up as well. This is a little more in-depth. All right, like I said, though, it's a lot going on, so I didn't want to confuse you right away. But as you turn here, you can even see the angle forming, right? And it tells you, right here, I'm at 90 degrees or 1/2 radians. And it shows you the values, right? And here you can see the values as they're moving along. So everything here is color-coded, right? So you got the blue line showing you your x values, showing you your cosine, right? So the cosine of 0 is 1. The sine of 0 is 0. And you can see how that gets manipulated as we rotate around our unit circle, right? All the way to 360 degrees. Right, so starting tomorrow, we're going to actually take a look at sine and cosine, and then the relationship between these two, and ways we can manipulate them to get us our other trigonometric functions. All right, any questions about that?